So in this movie, we're going to consider the reversal potential, what it is, and how it is generated. The reversal potential is another one of the features of the nervous system that students invariably have a difficult time understanding. It's not that difficult. I'm going to explain it to you. The experiments to reveal the reversal potential were designed to answer two related questions. First, what ions flow through the ligand-gated receptors at a synapse to generate an excitatory postsynaptic potential? And two, when an excitatory postsynaptic potential is evoked, what membrane potential is the cell trying to reach? The experiments I'm going to tell you about were conducted by Bernard Katz and his colleagues. The experiments Katz conducted revealed the basic events that occur during synaptic transmission. These experiments, together with those conducted by Hodgkin and Huxley, were the most important ever conducted on the nervous system. For this achievement, Katz was awarded the Nobel Prize in Medicine or Physiology in 1970. And one aspect of his experiments revealed the reversal potential that the membrane of a postsynaptic cell tries to reach when the receptors bind a neurotransmitter. The preparation Katz used in his experiments was the frog neuromuscular junction, the synapse that a motor neuron makes with a muscle fiber. The neurotransmitter released by the motor neuron at this synapse is acetylcholine, abbreviated as ACH. The specialized region of this synapse also has a special name, and it's called the endplate. The change in membrane potential that occurs as a consequence of the release of neurotransmitters, acetylcholine, also has a special name, the endplate potential, that I will illustrate in just a moment. However, the important point is the endplate potential is exactly the same as an excitatory postsynaptic potential. The only distinction is that the term endplate potential is reserved for the events at the neuromuscular junction, the synapse of a motor neuron with the muscle fiber, whereas the term excitatory postsynaptic potential is used for the events at synapses made by one neuron with another neuron. The basic features and events that occur, however, are exactly the same. When an action potential arrives at the end plate, the release of acetylcholine onto the muscle fiber first evokes an end plate potential, that is, the depolarization of the membrane at the end plate, and in turn triggers an action potential. Those events can also be evoked by an electrode that contains acetylcholine and puffing acetylcholine from the electrode onto the end plate. Watch. Depolarization, action potential. The end plate potential is generated here by the arrow, just below the axon terminal, and it's generated by the influx of positive charges through the open acetylcholine receptors. The action potentials, in contrast, are generated in the muscle fiber itself by the voltage-gated sodium and potassium channels that are embedded all along the muscle fiber. Here I'm going to illustrate that to you. We spritz on acetylcholine, generate an end plate potential. The end plate potential then triggers an action potential which propagates along the muscle fiber. But we are not interested in the action potential. We want to study the end plate potential without the confounding influence of an action potential. The end plate potential can be isolated by bathing the muscle in a solution containing tetrodotoxin, TTX, and tetraethylammonium, TEA, toxins that block the voltage-gated sodium and potassium channels, thereby preventing the generation of an action potential. Acetylcholine can then be puffed onto the membrane of the end plate to evoke a pure end plate potential. The action potential that would have been evoked if the solution bathing the muscle did not have a channel blocker is shown as the dashed gray line. There are three things about the end plate potential that I would point out. First, the end plate potential depolarizes the membrane to a value that is below 0 millivolts. It never reaches 0. Second, that value is still well above the threshold for generating an action potential. The threshold is indicated by the red line. Indeed, that is the very point. Every time the end plate potential is evoked, it drives the membrane to threshold and thus always evokes an action potential in the muscle fiber. The third point follows from the first 2 points, namely that normally the membrane never reaches the maximum value of the end plate potential because threshold is reached first and an action potential is generated. That is why the end plate has to be studied with toxins that block the actions of the voltage-gated sodium and voltage-gated potassium channels. The question that we want to answer is, what ions flow through the acetylcholine receptors to generate the end plate potential? Since we are interested in the currents that flow through the acetylcholine receptors, the synapse has to be studied in voltage clamp mode, because when the muscle fiber is voltage clamped, the currents flowing through the acetylcholine receptors are measured. And here is the arrangement. There is an electrode inserted into the muscle fiber that measures its membrane potential. There is a second electrode in the muscle fiber that can pass current to clamp the membrane potential at the desired membrane potential and to pass current to prevent the membrane potential from changing when the acetylcholine channels open. There is also a pipette filled with acetylcholine that we place next to the end plate so that the acetylcholine receptors can be opened when the acetylcholine is puffed onto the synapse. The first thing we do is clamp the membrane potential at some value, say minus 75 millivolts, by injecting current through the current passing electrode. The membrane potential is now set at that holding potential, in this case 75 millivolts, because that is the value to which we set it. Next, we puff acetylcholine onto the synapse and open acetylcholine receptors. Positive current then passes through the receptors that normally would depolarize the membrane, causing the end plate potential. However, the current passing electrode then passes an equal amount of negative current into the muscle fiber, which prevents the membrane potential from changing. The current that has to be injected into the muscle to prevent the membrane from changing is what we measure. Remember, the current that we passed is equal to the current flowing through the acetylcholine channels. In the next movie, I will first explain exactly what the reversal potential is, and then, second, I will show how the technique of voltage clamping was used to demonstrate the reversal potential and its value in millivolts.